Good afternoon, everyone. My name's Jim, and I work on the Neo4j database. And this afternoon, oh, that's a really bad angle for me. I can see my bald bit. Oh, no, guys, how deeply unflattering. Those lights just glint perfectly. Ruined. That's it. That's all I've got. I'm going to go and cry in a corner now. Thank you very much for inviting me to speak today. It's lovely to be here in Madrid. Actually, my first time in Madrid. It's a lovely place you've got here. So I'm visiting from just across the water in London. And today I really want to talk about the history of data. And I want to show how the history of data has been interesting, and I want to discuss a whole bunch of pertinent contemporary data issues that we're having today. And I want to introduce graph analytics to you. So those of us that went to do computer science at university will maybe remember graphs. And I can't see you very well, but I imagine the very thought of graphs brings fear to your mind. You had that professor, the guy with the arm patches, and the chalk, not a pen, the chalk, blah, 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 algorithms, blah, 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 breadth first search, blah, blah. And you were all sleeping through this, right? So don't worry, graphs are cool now. It turns out graphs are cool. They're not boring and academic like they used to be. They're now cool. But before we get to graphs, let's think about the old days. This is the old days, or actually it could even be a snapshot of Western Europe in 2014, but without the color photography. So the old days are a lot like today, except now we have Instagram. So the modern data era began in the 1970s. Oh, by the way, this is my favorite guy in the world. This guy here. Like everyone else is on strike. Fair enough, we can see that. It's the 1970s. It's very, very on strike. This guy is so on strike, he's not even going to remove his hands from his coat. That's how on strike this guy is. Your indignacios should be looking like this guy, for sure. Anyway, so the 1970s, apart from being an era of substantial political upheaval, were also the era when the modern database came of age. Sure, we had computers doing data processing before then, but it wasn't really until the 1970s, with the advent of the relational set of technologies, when modern databases came of age. And what's interesting about the 1970s is that we were all so similar. We were all so square. So in fact, the programming models given to us by relational databases made so much sense, because my payroll record and your payroll record were the same, and my social security entries and your social security entries were the same. We were really, really homogeneous. We were very tabular. We were like basically accountants. We were so boring. And of course, Generation Y changed all of that. So in the 70s, relational databases made a lot more sense. And in the 80s, relational databases really... she's dead. Is that too much? I don't know, because the lady stole my childhood, and I do bear a grudge. In the 1980s, the relational databases really took a strong hold. Something like by 1987, Oracle is the most valuable software company in the world, and the relational hegemony has taken over. At this point, when we say the database, we don't mean anything other than a relational database. And we are doing lots and lots of cool stuff with them. We're really starting to push the model forward, and they're becoming a really intrinsic part of our toolkit. Of course, though, relational databases have some problems. Thank you for sending me the schema, by the way. That's really useful. Several of you were like, oh, shit, how did you get my schema? The problem with relational databases, and bless you, some of you can look at that schema and you could understand the model behind it, can't you? You are so good at databases that you can do this. It's like looking through the matrix. All I see is green text on a black background. You guys can see kung fu. Bless you. You are so intellectually amazing. I look at this. I have no fucking idea what's going on with this shit. I am not even kidding. This is a bunch of babbling bullshit. This is just chock full of accidental complexity. So what we've done now is we've got so good at relational databases, we are just pushing the model above and beyond what it's comfortable doing. And tables are starting to suck. You've all done this. You've all done the 17 joins left, right, inside, outside, upper, outer, whatever they're called in relational mumbo jumbo, 17 times to this table to change this bit from true to false. Woohoo! Didn't that make you feel powerful? No, it made you feel pissed off. Because we're starting to get far beyond what the relational databases are comfortable with. That's why we have NoSQL. In fact, even at the most minuscule levels, relational databases inject a bunch of cumbersome idioms and abstractions into our code. Look at this. You guys know what this is, right? What's this? A join table. You know, when I first learned about join tables when I was a young nipper, I was like, fuck you, database, that's your job. Why do I have to tell you how to join your own data together? What do I pay for? I have to do the join table. Relational algebra didn't tell me about join tables, but then suddenly I pick up Ingress, yes, I'm that old, and I've got this join table nonsense to deal with. This is bad, because not only do you liberally pepper your relational database with all this accidental complexity, but then you actually have the temerity to join through them, and then you get this. This is what's known as a join bomb. Obviously, that's for dramatic effect. Your database won't necessarily, let's watch that again. Your database won't necessarily detonate, but so, here comes NoSQL. This is from the old days when you lot and my lot used to fight wars and the French used to join in now and again. NoSQL comes charging to the rescue. And in NoSQL, we have a bunch of really good technologies, mostly which are geared towards the problem of scale. Because, as the previous speaker noted, we're in an era now where we're producing so much data. And if only you could harvest some of that data, some even minute fraction of that data, and put it towards good use, there's going to be a lot of value. So in the NoSQL world, we have three main database categories. We have the key value stores, which have a really nice programming model, the hash map. Really, really simple to work with. We have the column stores, a bit more of a sophisticated data model. It's a nested hash map of hash maps, but where we get more insight into the data, since where the keys in those hash maps line up, we get a kind of natural index emerging. And I'm sure across this room, the debate rages about which is the most scalable of the column stores. Is it Apache Cassandra? Is it HBase? Is it that thing that we built for our own web app? Blah, blah, blah. I actually know the answer to this. This is the one piece of empirical data I have for you. The most scalable column store that I know is this. It's a British museum. It has columns, and it's where we store all of the things that we stole. And when we want to scale it out, we simply build another wing and put in more stuff that we stole. Come and visit, it's lovely. And then finally, and not leastly, we have the document databases, as exemplified by the likes of MongoDB and CouchDB, BaseDB, Couch thing, I don't know, whatever it's called today. And these things have a really nice idiom insofar as they act like filing cabinets. You can put documents in, take documents out, you can index them. Very, very nice idiom. What Fowler and Sadler's observe in their book, NoSQL Distilled, is that these three kinds of databases actually have a kind of common ancestry or common idiom, which is that they are aggregates. As you store and retrieve atomic disconnected data. And Fowler and Sadler's observe in their book, it's a great book, by the way, very thin, you can read it on the bus to work, it's really very lovely, that these databases work really, really well when the storage and retrieval patterns are symmetric. Store a shopping basket, retrieve a shopping basket works brilliantly. Store a product, retrieve a product works brilliantly, and so on and so on. But where you want to slice and dice data, you tend to have to resort to a compute-intensive mode of gaining insight. So you pull the data out of the database, you run it through some computational infrastructure, and then you gain your answer. And that's a bit different from what we're used to. We're used to building a model, even in a relational database, we're used to building a high-fidelity model, asking a question of that model, and gaining insight that way. So we could use those technologies to power connected data, but as Harrison said, I've got a bad feeling about this. So imagine that we had an aggregate database and we had some users in there, some kind of real-world people. And you clever humans, you can see that there is some linkage between these people. So you've got this guy called Gaza, and he's a friend of this guy called Jeff. And this guy called Jeff is a friend of this guy called Sally, and he's also a friend of this guy called Gaza. That's nice. And then Sally is a friend of Jeff and a friend of Funky Sam, and Funky Sam is a friend of Sally. So you guys, with your clever human inference brains, you can understand what this means. And indeed, if you wanted to, you could even run some computational processes over the database and reify out of that database a bunch of linkage. so that you can start to understand the connections between these applications. In a graph database, you don't do that. In a graph database, you store those connections natively. So in a graph database, you might have, you might have actually these linkages stored on disk so that the cost of joins, if you will, becomes incredibly cheap. You can also then start to enforce some levels of consistency. For example, in the aggregate, if I remove this guy, Gaza, is it my responsibility also to remove this property here? Maybe, maybe not. Certainly the database doesn't care because that's not what it's designed for. Whoops. So in a more sophisticated scenario, if I want to look at purchasing, this stuff is trivial to do in a graph database. It's a bit more difficult in the aggregate. I mean, firstly, what's my modeling idiom? Do I have separate product records and separate customer records? Do I inline products in customers? What do I do? Do I have separate indexes for them? It's actually a relatively complex challenge, and also one that tends to be algorithmically complex, in order to try and store this kind of data in an aggregate. In a graph, it's dead easy. You can even read this. Gaza purchased supercans. Sally purchased Cooldex, Sally purchased supercans. If you wanted to infer something from that, if you wanted to make the most trivial retail recommendation, you can see that people who purchase supercans also purchase Cooldex, therefore tell Gaza to buy some Cooldex. Trivial stuff, right? Except in a graph database, it really is trivial, whereas if you have to crunch this stuff yourself, it's way, way harder. If we went one level further out and started to do social selling, what are the kind of things that my friends and my friends of friends have bought because I should buy them? Turns out that's ridiculously effective, by the way, for recommendations. Peer pressure makes us buy the most inane shit all the time. Just because your friends and their friends have something, you end up with one. We suck as a species. So in this case, you can see that I want to look at what Gaza's friends and friends have bought. So Gaza is a friend of Jeff, who's a friend of Sally, and Sally has bought supercans and Cooldex. Doing this in a graph database like Neo4j, the one I work on, is super, super quick. I can traverse on my laptop, which is nothing special, about 13 million of these per second. So you can see you can explore an awful lot of graph in sufficient real time to make a difference to people in the clickstream, which is awesome. I could just watch this actually for hours. It's quite hypnotic. So we're at an interesting kind of crossroads, really. My colleague Alistair Jones calls this a relational crossroads. Straight ahead is relational databases. That's a dead end for most of us. On the left, we denormalize our data model. So we take our rich domain model and we denormalize it into keys and values or documents or whatever, and then accept that we have a compute-centric model to gain insight from that. On the right, we have the graph databases, where compared to relational, we have a far more expressive model. We have richly connected structured data, and it's by traversing over that structured data that we find insight. So who's doing this? Actually, lots of people are doing this, which is great, because I need to pay the rent. So you've got people like telecoms companies like Telenor. Telenor had a solution, had a problem rather, where they were trying to manage business users' mobile subscriptions. And you can imagine that in your business, there is a whole weird hierarchy of levels and who can use what and who blah, 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 blah. You superimpose that onto the telephony graph, on the product graph, and so on, and you've got a massively complex intermingled data set where in order to find your specific permissions, which services you can access on their mobile network, takes a whole bunch of compute if you're doing it in traditional data sources. In this case, Telenor used to have a SQL database trying to mimic this path relation. Is there a path between Jim and the service Jim is trying to access? And it would take several minutes to run. Not good enough when I'm logging in. They changed this to a native graph solution on Neo4j. It takes milliseconds now, so I can run this stuff in the clickstream. We've got folks like Beamlee, who are interested in social television. So while you're watching TV, you're also doing something on your iPad with other Beamlee users. I mean, my father would disapprove. You have one screen at a time. But apparently young people like this stuff. I'm somewhere in the middle. And actually what they want to do is keep a graph, or they want to keep some metadata about TV shows. But it turns out TV shows are really complex. It's not just the one TV show, which is Doctor Who on Saturday evenings on the BBC, but that episode of Doctor Who is repeated the following day on another channel. And then it's sold to BBC America, and it comes to Spain, and blah, 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 blah. And there's a whole graph of metadata about the provenance of this episode. And they want to be able to hook into that. They want to be able to hook into TV schedules and make recommendations. Socially, they want to be able to see what people like you are doing, what people like you are watching, and recommend based on that metadata. They had a system, again, written in SQL, abysmal to migrate because the model got more and more and more complex as they went on, slower and slower and slower. Migrate this to a graph, which is what it is naturally, and then suddenly, boom, easy to migrate, super fast in the clickstream. eBay, big blue chip vendor, were interested in delivery. They recently acquired a London-based startup called Shuttle. And what Shuttle were doing is aggregating courier bandwidth, so physical couriers in the market in real time. And what their goal is for me to be able to shop on eBay, buy something from you, and then have that delivered to me at a mutually convenient time by aggregating courier bandwidth. They started doing this on MySQL, and what they found was that the latency of their longest query was larger than their shortest physical delivery. That is insane. Something in the real world was faster than something in computer world. How does that even happen in the 21st century? Computers are quick. I mean, these guys aren't using Sinclair Spectrums to do this. But what they observe is actually routing is a graph problem. It's one of those graph problems that we had to suffer at university when the old guy was blah, 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 Dijkstra, blah, 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 centrality, blah, 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 A star. Remember that guy? Yeah, he comes back. But it turns out now they can return not just one convenient time slot to have my stuff delivered from your house to my house, but in about a second, they can return 75 time slots. So I can say 1 to 115, 115 to 120, 125 to 130, blah, 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 blah. Click, that one is for me. The customer experience is fantastic. I've used this in London to move a refrigerator across the city at a time of my choosing. And it was dead cheap, and it was really, really good. Moving on from eBay, you've actually got Europe's largest parcel network. Again, another graph problem. The problem that these guys had is the largest parcel network in Europe, and the problem they had is that their existing solution was built on a relational database, the queries weren't scaling, and by the time Christmas was coming along, there would not be enough vertical or horizontal capacity in the database to support delivery. In this country, there would be no Christmas. Poor kids, man. So they replaced their legacy SQL system with a graph. They replaced it with Neo4j. And it turns out parcels are really cool. I didn't know this until I started working with these guys. You think in order to cancel a parcel, it has to go all the way to your house, and then you say, no, I don't want this anymore, and you have to walk to the post office and hand it back and fill in a form. But no, oh, no, no, no. As the parcel is moving through the parcel network, you can now click cancel, and it's on the fly rerouted back to the sender. This is okay, it's not quite jetpacks, but it really is a little bit like living in the future. So they were doing this at massive scale, and so Europe's largest parcel network are doing this, and as parcels are flying down the conveyor belts and being scanned, they're being routed and changed and blah, blah, blah. It's absolutely amazing to see effectively kind of all that IoT technology and all that mechanical stuff brought together in the graph. Phenomenal. And one day I saw the guy who built this, the chief architect of this stuff, talking about it at a conference, and a guy from Oracle stood up in the audience and said, yes, well, Oracle can clearly do this. Why on earth would you use a graph? And really started to argue the case for going back to Oracle, actually. And the architect was a very, very polite German guy, and he basically said, while you've been arguing with me, my system has just routed 10,000 packages. Please sit down. Which I thought was beautiful. And then you've got people like Crunchbase who are building the network of entrepreneurs and businesses and blah, blah, blah. Such an obviously embarrassingly graph problem about all the promiscuous startup founders and their sources of money and blah, blah, blah in the United States. And one that I particularly love, actually, Just Giving. They are a social firm. What they want to do is encourage people to give to charitable causes. And the way they do that is by doing social analyses. These guys are doing things like Triadic Closures. They're looking for centrality, looking for important people in the graph and so on. These people are doing amazing stuff. And just simply because they understand the power of a network. If you're embedded in a network, your effects are amplified. So if you're doing some charity fundraising, your friends will get behind you. If you are a famous figure doing some charity fundraising, you can get whole countries behind you, all because effects are amplified out through the network. And these guys didn't have to invent their own analytics, because it turns out graph theory is so well established as a discipline, they could just look it up in a book. How? Because all this stuff is graph native. And when you realize the power of graphs and graph theory, you can start to get some amazing stuff done. So let's start to look at analytics. And the first part of analytics I want to look at is this notion of local properties. Graphs are a bit perverse. They really are. I love them, but they're a bit perverse. In the graph, it's small things which unnaturally affect, disproportionately affect the overall structure of the graph. And in the graph, it's weak things that naturally affect the overall structure of the graph. It's not the big and the strong, it's the small and the weak. It's kind of a Christian fable, really. I mean, Jesus, if he'd exist, would love this. Oh, Catholic country, be careful, Jim. Now we found the limit. Okay, so you liberal elite, you. Local properties. Oh, this is a local property where I live. I love this. It sells Turkish, Greek. I mean, I don't know how they get both of those in the same room. And Mediterranean food. If you're feeling hungry, the Greek guy in the audience gets that. And, by the way, if you're in the mood for something very, very, very plain, you can also buy English food. Great stuff. So, local properties. The first local property I want to talk about is this thing called Triadic Closure. And Triadic Closure is the way that graph theorists call it because they're too embarrassed to say make triangles. So it's kind of like the Haskell guys, right? They won't, have you ever heard them say that special word that they have? They always say it with the Harry Potter voice. Monads. This is the monad equivalent for graph theory. Literally, graphs, particularly graphs involving humans, have this innate tendency in them to want to make triangles. You see this here, right? This is an example from the South Park cartoon. I'm a big fan. You've got this young lad called Kyle, and he's a friend of Stan, and he's a friend of Kenny. And you've seen this in your own social networks as well, right? You know two people, you like them both, so it's a natural thing that at some point they're going to meet, and because you've kind of vetted them, they're probably going to get on. They're probably going to like each other. Because it's awkward not to, right? So you provide a kind of transitive trust between those people. So in the graph world, there's a natural tendency to want to close off this gap and make a triangle. And this is what we call a triadic closure. So when Stan and Kenny become friends, we've now formed a triadic closure. Then there's this notion of structural balance. So not only do we want to make triangles, but we want to make triangles that are structurally balanced. That is to say, that they feel right. They're a low energy structure. So see in this case, we've got Cartman, who's a friend of Craig, and he's an enemy of Tweak. In fact, there's a whole episode where Cartman, who frankly is a bit of a dick, wants to make Craig and Tweak have a fight. That's the whole episode. Kids aren't cool, right? Kids are not cool. They do this shit for real. They are nasty. And so one way we could make a triadic closure would be this. We could say that Cartman is a friend of Craig, Cartman is an enemy of Tweak, and Craig and Tweak are friends. That's a closure, right? It's a triangle, but it doesn't feel quite right, yeah? Because Cartman says to Craig, hey, Craig, like, let me try. Hey, Craig, Tweak is such a total douchebag. Come on, for an Englishman, that's not bad, right? And I can't do Craig. Craig's like, no, Cartman, Tweak's my friend. I like Tweak. Like, leave him alone. Don't pick on him. So this is awkward, right? This triangle doesn't feel stable. The graph resists it. It's like, no, I don't like this. What is a balanced, or a structurally balanced closure is this, where Cartman is friends with Craig, and Cartman is an enemy of Tweak, and Craig and Tweak are enemies. This, look, from a moral point of view, this is not nice, right? Because it shouldn't be the case that Cartman and Craig can gang up on Tweak, but from a triadic closure point of view, we call this structurally balanced because it's a low energy state. So these guys, hey, I hate Craig, I hate Tweak, yeah, Cartman, I hate Tweak as well, let's beat him up, is what this triangle says. And poor Tweak is over on his own, he's got no friends, nothing in the graph is supporting him. So that kind of sucks, actually, if you're Tweak, but from a graph theory point of view, this stuff is very useful. Of course, a better balanced closure from a moral point of view is this one, where everyone is friends. So it turns out, and you can feel this, right? If everyone's friends, there's no agitation in the graph. So it turns out there are two possible balanced closures. One where you have everyone is friends, and the other one where you have two negatives, two enemies and one friend. And they're both stable structures in the graph. The graph doesn't want to change those. So this is a key predictive technique. You can take a graph and you can iterate over it looking for opportunities to make structurally balanced closures. The graph will mutate and you can see what happens in the end state. Now, it turns out that we can do something about this. We can kind of demonstrate this. So this is an example taken from a book called Networks, Crowds and Markets. It is by far and away the best academic book you will ever read. Go ahead and download it. It's amazing. It's about graph theory and game theory. It's absolutely brilliant. And this is a graph of it's from around the mid-1800s of the great houses of Europe. Sorry that you guys aren't on this, but it turns out as we go through time, you'll find out you've got your own little side story going on. A rather tragic side story, actually. And so in this graph, the red connections, the red relationships represent enemies, and the black relations represent friendship. So in fact, historically, this graph here is known as the Three Emperors League, because you can see we've got the emperors of Austria, Germany, and Russia all allied, and then everyone else hates each other, except Italy, who's sitting out on the sidelines. So you may giggle, Italy gets stuck in a minute. So what can we do with this? Well, actually, we could look for opportunities to make triangles. We don't care that these are the great houses of Europe. We don't care that there's a bunch of contemporary European politics that we can discuss here. We care that we're just going to make structurally balanced closures in the graph. Brilliant, so let's do that. Let's bring Italy in. We've now made a structurally balanced closure involving Germany and Austria. And you can kind of see that kind of works, right? Because you've got a stable friend, friend, friend triangle. Cool, okay. So what's our next opportunity for making a triadic closure? Well, we can start to bring in, the German-Russian laps. So now Germany and Russia are at each other's throats. Brilliant. Come on, don't break now. Weirdly, France and Russia become friends. But the graph doesn't like this. Well, it does actually at the moment. The fact is, the graph likes this because France and Russia can now gang up on the UK. Hey, Russia, let's get Britain. Yeah, that's a really good idea, France. Let's go get them. I mean, obviously, the graph also can't predict how rubbish France are at wars, so it's not entirely historically accurate. Ooh, salut mes amis français. So, this is kind of cool. This is kind of weird. Remember, this means friendship. Okay, admittedly, this is around the time you guys are starting to get pissed off on the sidelines as well. This relationship here represents something called the Entente Cordiale. And my schoolboy French, I remember the translation of this very well. It actually means, Britain, we surrender, please stop beating us. Taking a few liberties with the translation there. This is really weird, because of course the French and the Brits have been enemies for a millennia at this point. So this is odd. The graph does not like this. Not at all. You can see, France says to Russia, hey, Russia, my friend, the UK is awesome. And Russia's like, no, don't like the UK. And it's an awkward thing. The graph is going to reject this unstable closure. And in fact, what happens is that the UK becomes friends with Russia, and then we carry on simply iterating over the graph, making stable, structurally balanced triadic closures until we end up here. You'll see now that the graph is at a naturally low energy state. All of these are structurally balanced closures. Over on the left side, you see, let's call them the good guys. And over on the right side, let's call them the bad guys. And all we have in between them is enemy of relationships. So graph theory is able to predict the outbreak of the Great War, which from a graph theoretical point of view is like, fuck yeah! And from a purely humanist point of view, is one of the greatest human tragedies ever to have afflicted this continent and this planet. Bit sad because it's the 100th anniversary this year, right? So you could do this, but you don't have to do this in such macabre terms. You can do this for your business. You can look for all kinds of very surprising things in your data simply by applying this kind of, it's a very surprising thing. Ooh. I'm amazed. I'm amazed at graph theory. Oh. One more. I'm amazed that graph theory can do this kind of stuff. Then there's another interesting local property that we can look at called strong triadic closure. In fact, it's about not just positive and negative sentiments, but the strength of those sentiments. So if we see these same triadic closures again, so here we have Kenny and Stan. Kenny's a nice guy. He's kind of friends with everyone. He's a good guy. Kenny's friends with Stan. Kenny's friends with Cartman. Stan and Cartman, they're not enemies. But Cartman's a bit of a dick. Stan doesn't like him that much. It's kind of, I'm sort of a friend. So there's this kind of notion of strength in a relationship as well as sentiment. And we can put this to use because it turns out that these weak links often provide bridges between different domains in a graph. It's why you rarely get to hear of a new job from your direct social circle. Those guys know everything you know already. You tend to find out about a new job opportunity through a friend of a friend in a different part of your social network, typically in a more distant or weaker neighborhood. So we can do this. So this is a network of an elementary school, so for kids like at 8 or 9 years old. Interestingly, it could also be the graph of IT, because as you can see, the boys are up here and the girls are over here, and they don't really talk. So it could be us. Here you see this guy, Stan and Wendy. Stan and Wendy are kind of boyfriend and girlfriend, you know, but kids, it's awkward for kids. Or indeed, awkward for IT people to express sentiment, right? You can write beautiful code poetry, but if you approach someone that you have a crush on, blah, 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 you know how it is. It's a geek thing, kind of geek autism. So we can use this property, though, to start to analyze a network. We can start to look at how a network might form triangles, but we can also start to look at how the network might bifurcate, how it might split over time. And here's an example from the 1977 the American Journal of Anthropology. The cold winter evenings in my house fly by. This is a university karate club. And what's happened is that this guy, number one, formed a karate club. He's a student instructor, the original president of the club, and the club grew. And eventually the club grew so much that they needed to employ a professional instructor to help with the tuition. That's this guy, number 34. And as you can see, kind of even visually, there are two clumps in this graph, two distinct neighborhoods where there's a bunch of people who are more embedded around this guy and a bunch of people who are more embedded around this guy. So we can start to use some of these weak links, looking for weak links, to partition the graph and see how the club might actually start to bifurcate over time, how the factions might modify themselves. It would be useful, for example, in geopolitics in the Middle East right now to be able to do this. So graph theory can actually predict this. By looking at how embedded someone is in a particular part of the network, we can start to pick that network apart and look for how the graph might disintegrate. Graph theory, if you apply some of these algorithms, will predict this bifurcation. So the guys shaded in red end up splitting off in a new club with the original student president. The guys shaded in white end up splitting off in a new club run by the professional instructor. And you can see this, right? You can see that number 33 here is mostly connected, in fact, exclusively connected with people who are himself with the professional instructor. He's not directly connected at all with the student instructor, and most of his friends are in this clump. And you can pick apart this and do that. However, in picking apart this graph, there are things that graph theory can't take into account. In fact, graph theory gets it wrong. After all those minutes of telling you how awesome graph theory can get it wrong. Yes. And here's the change. This is what actually happened. This is what actually happened in 1978. The split happened this way. And node number 9 did not do what graph theory predicted. Why? Because what graph theory doesn't know is that number 9 was 2 weeks away from earning his black belt under the instruction of this guy. So it made more sense for him to stay with this guy rather than split off and go with the new club. Of course, if we'd added more dimensions into the data, our prediction would have been better. If we'd given it more processing power, our prediction would have been better. But graph theory provides statistically brilliant predictive analytics, but they're not totally foolproof. So then the other thing we can do in graphs is we can do predictive analytics, but we can also do retrospective real-time analytics. We can start to look for patterns in our graph data, look for structural patterns and value patterns in our graph data to answer questions in real time, in the clickstream, in the web request, in the web response. And who does things like this? Oh, I don't know. Facebook. So for example, we might start to formulate questions like, in which sushi restaurants in New York City do my friends like? That's a really interesting question, and in fact, it's a far more powerful question than what are the best sushi restaurants in New York City? You see the difference there, one of which just draws on some arbitrary data that I probably am not invested in. But the restaurants that my friends like, and my friends are likely to have broadly similar tastes to me, is going to provide me with a much better, much more tailored answer to this problem than just saying to Google, good sushi restaurants in New York. Now, in order to graph that, it's pretty straightforward. There's me. I told you I like Eric Cartman. He's kind of a boyhood hero. And you can see that I'm a friend of Andreas and I'm a friend of Michael. And you can then see that Andreas likes sushi zam and Michael likes iSushi. They both serve the cuisine sushi, and they're both located in New York. Admittedly, this is somewhat of a poor geospatial index. In a real thing, it would be made out of R-trees or something. So there's a really nice graph structure there. If I traverse looking for that pattern, I'm going to end up finding at least 2 sushi restaurants in New York City that my friends like. So how do I query that? Do I write SQL, and it's like select sushi restaurants from joined. How long is this query going to take to run again? No, let's not do that. Am I going to decompose this into key values and do a bunch of work in the application? No, because it turns out that when you've got a graph, any decent query naturally emerges as a consequence of the structure of the graph. This is one way that we might query that graph. And here you can see, effectively, we've got ASCII art for graphs. This is called Cypher. It's Neo4j's query language. And what we're saying here is, find this, hey, database, find me this pattern where I've got a node which has an outgoing friend of relationship to something I don't care about, who likes who has an outgoing likes relationship to some restaurant, which itself has an outgoing located in relationship to some city, and where the restaurant serves a particular cuisine. And then I'm going to bind some of these. I'm going to say, well, the node represented by the identifier me is bound to the name Jim. The city has to have a location property called New York, and the cuisine has to have a cuisine property called sushi. Give me back the restaurants. Easy. So effectively, once you've got your graph drawn on the whiteboard, you just need one special purpose tool in order to reify out the queries. And that special purpose tool is called a different colored pen. And you sketch the ASCII art on top of the graph, and that is 90% of your query done. You can now simplify this. You can add labels. So Neo4j2 supports the notion of labels, tags or types or whatever you will. They declare the semantic role of a node in the network. So now this is a bit richer. You can see that I want a person who's a friend of another person who likes a particular kind of restaurant in a particular place which serves a particular cuisine. And then you can inline most of that to make the query shorter. And now this is far more readable. Hey, database, find me some person has the name Jim who has an outgoing is friend of relationship to some other person, where that person has an outgoing likes relationship to some restaurant, where that restaurant is located in some place, where that place's location is New York, and where that restaurant has an outgoing serves relationship to a cuisine, where the cuisine is bound to sushi. Give me the sushi restaurants. Wow. That is probably the smallest and most effective retail recommendation that you could buy. My colleague Max DeMasi, having seen Facebook Graph Search, which is what this mimics, was amazed by it. So this is great. It's got natural language processing. You type questions in. You get answers back. This is brilliant. And he fully admits to being in a really, really brilliant situation. He said, I was clueless and stupid and therefore powerful. And so what he did was he brought together a bunch of Ruby natural language programming processing libraries. He brought Neo4j in. He harvested a bunch of Facebook data from himself and his social network, and he stuck all this in Neo4j. It took him a weekend to build this. Max is a good programmer. It'd probably take me a week. But he did this in a weekend. So he built something that was actually functionally better than Facebook Graph Search in one weekend. His natural language queries produced these kind of Cypher queries that we're seeing here. So he was able to type using English, and the English would map it down to this kind of Cypher structure, fire the Cypher queries up at the database. The database would then grind through the data looking for matches. Remember, I can traverse about 13 million of these per second on a laptop, so you get an awful lot of graph quickly, and then the answers would come back. This is so cool. So, why, admittedly, Facebook's implementation of this is probably a bit more scalable, but then Max built this in a weekend on Neo4j, and even on Max's unoptimized system, remember, you can traverse about 13 million relationships per second. And it doesn't matter in a graph how big your data grows. You're not penalized for that other than by spending bytes on disk, because the latency of a graph query is proportional to how much of the graph you choose to search. It is not proportional to how much data is in the database. There are no Cartesian products here. There are no set joins going on, which means that even if you've got gazillions and gazillions and gazillions of relationships and nodes in your database, and your query happens to only touch a few thousands of them, you're going to get latency that's proportional to a few thousands. Of course, if you want to build an algorithm that touches every part of your graph, then the latency will increase. So if you build PageRank or something, your latency will go up because that algorithm needs to touch all of the graph. But for most egocentric queries, that is, hey, user logs in, we now bound the search to the user and look for interesting information centered on that user. These things tend to take milliseconds. So you've got an awful lot of headroom, even in a teeny-weeny laptop, for doing some very sophisticated graph analyses, or indeed for serving many, many concurrent requests for shallower analyses. So this stuff's really, really cool for real-time computing. We just heard from Amazon about how real-time computing is implemented on their platform. And graphs are such a good candidate for real-time computing because they allow you to choose effectively how much time you want to spend looking for an answer. You can choose and tune how good you want that answer to be. Do you want an approximate answer, which you can retrieve in a handful of millis or nanos? Or do you want to do some more thorough searching? Do you want to explore more or less of the graph? Do you want to bring in more or fewer dimensions? How much of the graph do you want to explore equals how long you want the query to run. So you can, if you know that your user will happily wait twiddling their thumbs for 10 seconds, oh boy, you can do an awful, awful lot of graph analyses in 10 seconds. If you know that you've got an impatient user on a mobile device where battery life is important and they can only wait for 100 millis, well then you can tune your query to be statistically good for them. As we get to the end now, I would point out that don't be afraid of graphs. A lot of folks, like myself, we came from a SQL background, we encountered graphs, and you just think, oh my God, this is hard. This conjures up memories of algorithms and data structures and all that kind of like big O nonsense. We don't like that. This sucks. When I first encountered graphs, when I first encountered Neo4j, in fact, I was working at a telecoms company, and the problem we were trying to solve was upsell and cross-sell. And we had elected, before my time, I hasten to add, we had elected to buy a system off the shelf and then spend several years customizing that system, which, as everyone in IT knows, almost never goes wrong. Ever. Buy and then customize. It's like all the problems of buy and all the problems of build multiplied. Anyway, we were doing that, and I thought, well, the most important thing that the business wanted was upsell. So when you phone into the call center, oh, hi Jim, nice to hear from you again, blah, 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 blah. Oh, so I see that you have premium, I see you have basic internet at home. Would you like to try premium internet? Oh, yes, I would, thank you very much, that kind of thing. That was so important to the business, and in our project plan, they were going to get this to around year 3. So we bought some stuff, we started customizing on it, and just 3 short years later, they would get the thing they really wanted. So I heard about this thing called Neo4j. I bumped into this guy somewhere in Sweden, and he started telling me how there were graphs in my data. And I was like, do you know how a database works? There are tables. And he's like, no, you can do graphs. I'm like, you're an idiot. Leave IT now. You are a complete idiot. And he's like, no, honestly, blah, 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 upsell, blah, blah, blah. I'm like, no, you're drunk, and you're an idiot, and I don't like you. Funny story, that guy's my boss now. So maybe he had some points. So I went back to work. I thought, oh, actually, that guy who annoyed me saying there were graphs in my data, he's right, because I've got this product, and this other product depends on it. So if I've got basic internet, that depends on having a modem or a set-top box, and premium internet depends on basic internet. So it's like a dependency graph. And I thought, oh, that guy's kind of right. Oh, I get it now. Okay, so what was that guy's stupid product again? Neo4j, Java, Neo, Matrix, I don't know, some shit like that. So you just Google graph database and this stupidly named thing comes up, right? Neo4j. I mean, how 1990s is that? Oh, okay, that weird guy told me to try this. So I tried it. So I poured all of the data that we had into it and all of the data about customers and the stuff they owned. And I made little graphs of what depended on what. And then I asked it a question. I said, dear database, I already have basic internet. What can I be upsold? And boom, moments later, it came back and it said, you can have premium internet, you can have digital phone, and you can have voicemail. So what it had done is it found the common ancestor, which was that I had a modem. And it said from that, I could get basic internet, which I already had, premium internet, which I didn't. But it also noticed that digital phone depends on modem, and voicemail depends on digital phone, depends on modem. So it tried to sell me these things as well. For a fleeting second, I thought, holy shit, I built Skynet. Then I realized that all I was doing there was a graph traversal. I was simply doing actually a breadth-first search through my local graph to see what things that my products were connected to, and I was getting them recommended. The biggest concern I had with this was that I'd done it wrong. I did this in an afternoon. It was a long afternoon. It took me several hours, but it was just an afternoon. And it gave me that answer, and initially, wow, this is amazing. And I was like, no, that was too easy. Where's my first normal form? Where's my second normal form? Where's my third normal form? Where's my BN normal form? Where's my blah, 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 blah? There were no rails. I didn't feel like I'd done enough hard work to achieve the result. And I was plagued by doubt because I simply thought I'd done it wrong and I was going to get shitty answers from my data. But then over time, we worked on this data and we were getting the right answers, and it just occurred to us, yeah, actually, once you get over this hump of self-doubt, you end up here. And you just find that graphs are a really pleasant, easy idiom to work with. So if you come along to my session this afternoon, I'm going to do some live coding. I'm going to show you how graphs really, really are very pleasant and comfortable and convenient to work with. And it turns out you already know graphs. You just don't know that you know it. Since then, there's been an awful lot of stuff. So I recommend you, this stuff's all free. There's a book on graph databases that I wrote with Ian Robinson. And there's a new book called Learning Neo4j by Rick Van Bruggen. And there's an online course, How to Learn Neo4j. They're all free. You can get these things as free ebooks. Point your browsers at those URIs, download those ebooks for free, have a read, enjoy, learn. You don't have to go through the same steep learning curve that I did, because we wrote down what to do. We gave you the instructions. So please do get stuck in. And remember that when you switch to graph tech, problems that previously looked impractical or impossible start to become very possible. In fact, when you switch to graph tech, you start to find that things that looked impossible are nothing. Because impossible isn't a fact, impossible isn't opinion, impossible is a declaration, it's a dare, it's a challenge. And when you switch to graphs, you find that impossible is potential, and in fact, impossible is nothing. Enjoy graphs. It's lovely being here with you. Come along this afternoon to the Neo workshop, and we'll do some more graphing. Thank you very much for listening.